In the last video, we talked about stability and long-time behavior for difference equations. Now we're going to do it for first-order ordinary differential equations, systems of differential equations. The overall picture is very much the same, but some of the details are different. So first of all, when you have a system of differential equations, you wind up with behaviors like e to the lambda t. So suppose you had a vector whose entries were 0.01 e to the 2t, e to the 1 plus it, and e to the 1 minus it, and then the difference of the complex exponentials divided by 2i, and then a million e to the minus 3t. And I ask you, what does this do in the long run? Well, you'd notice that this term grows, and these terms grow. These grow and oscillate, but they grow, and this term shrinks. So if you expanded it out like this, you'd say, I've got a term that grows, a term that grows, a term that grows. You know, the sum of the complex exponentials and differences wind up turning into exponential times cosine and exponential times sine. And then a term that shrinks. And so in the long run, you wind up with something that behaves like the term that grows the fastest. E to the 2t grows faster than e to the t. This term shrinks away. This term shrinks. These terms grow slowly. And this term grows quickly. So in the long run, this term is going to be the biggest term, and eventually the vector is going to be pointing more or less in the E1 direction and is going to be growing like e to the 2t. So in general, when you've got a system of ordinary differential equations, dx dt equals a matrix times x, we know that the solution is a linear combination of terms where the terms are e to the eigenvalue times t times the eigenvector. And we say, hey, if we have an eigenvalue, call it a, and it's positive, then e to the at grows, and we call that unstable. If the eigenvalue is negative, then e to the at shrinks, and we call that stable. And if the eigenvalue is 0, then e to the at is just 1, and we call that neutral or borderline. But that's leaving something out. And the thing that's left out is complex eigenvalues. Eigenvalues don't have to be real numbers. They can have real and imaginary parts. So if you have an eigenvalue that's a plus bi, then we have to look at what is e to the lambda t. How does that behave? And we split it up as e to the at and e to the bit. And e to the bit is cosine of bt plus I sine of bt. This oscillates. The real part goes up and down and up and down and up and down, and the imaginary part goes up and down and up and down and up and down. The whole thing oscillates, but the whole thing grows like e to the at. So it grows if a is positive. It shrinks if a is negative. It's borderline if a is 0. In other words, if the real part of the eigenvalue is positive, it will grow no matter what the imaginary part is. If the real part is negative, it will shrink no matter what the imaginary part is. If the real part is 0, it'll be neutral no matter what the imaginary part is. So now let's go back and look at our original picture. We had these terms that went as e to the 1 plus it and e to the 1 minus it. E to the 1 plus it is e to the 1t, and then you have an e to the it that's cosine plus I sine. E to the minus I is cosine minus I sine, and they add it up to give you 2 cosine. And likewise, here you have things that grow as e to the 1t and e to the 1t, and they happen to cancel and give you exactly sine. But the point is that this 1, the real part of the eigenvalue, tells you how fast it grows. This is less than 2, which is the real part of that eigenvalue, so this term grows faster than these terms. The dominant eigenvalue is always the eigenvalue with the greatest real part. 2 is bigger than 1. And by the way, I'm not saying the greatest in absolute value. 2 is bigger than negative 5. Negative 5 would be stable. You would have something that shrinks. 2 grows. So the eigenvalue with the greatest real part is the dominant eigenvalue, and that gives you the term that grows the fastest or shrinks the slowest, and it's what your system will look like in the long run. So here's the picture in the complex plane of what's stable and what's unstable. The whole right half plane is unstable. Anything with a positive real part is unstable. Anything with a negative real part, the left half plane, is stable. And the neutral ones are the ones with zero real part. In other words, exactly the imaginary axis. 3i is neutral. Negative 5i is neutral. 0 is neutral. And just as with difference equations, for a system to be stable, you have to have all of the modes stable. In other words, all of the eigenvalues have to be in the left-hand side. Okay. So this picture is where you have the biggest difference between differential equations and difference equations. For difference equations, we had inside the unit circle, outside the unit circle, on the unit circle. For differential equations, you have the right half plane, the left half plane, and the imaginary axis.